So talking about how to provide GNS signals within an underground area where, of course, satellites cannot reach. So, but why is it beneficial to have GNS in these underground areas or underground mines? Well, there's a number of reasons, which is related to why do you even use GNSS in open sky? Comes down to precision time. Many instruments and communication systems use the time source from the satellites today. So by having that in these areas certainly is a benefit. So it's being able to synchronize for any critical events, but also location of assets, whether they be people, vehicles, tools, other equipment, and then navigation, being able to track and measure certain performance parameters around different vehicles, and of course safety, that is being able to provide safe egress in emergency situations. So how does our system, NoSky, support standard off-the-shelf GPS receivers? Number one is you don't have to have a special receiver at all. You can use a standard receiver. So the way to make this system function is you've got to understand how a GPS receiver actually does calculate its location. It uses the time of travel from the satellite to the antenna on your receiver. And that signal that's coming from the satellites, there's 4 main components, but there's only 3 of those that we actually are concerned about. One is called the course acquisition code. And then there's the GPS system date and time, which is the universal time code, UTC. And then there's a lot of data in regards to the satellite itself, and that is the almanac, the ephemeris, satellite health, satellite clock corrections. The almanac is like a star chart, and the ephemeris is precise information about that satellite location, where it is in the skies. We won't worry about the P code. That's typically used for military systems. So basically, the receiver calculates the time of travel, uses what's known as the CA code, which is a pseudo-random code. And adjusting that code allows for different locations to be calculated by the receiver. And this is what we rely on. Just to give you an idea of what the ephemeris information is provided from the satellites, it tells us everything about the flight of the satellite, its exact location, all relative to the center of the Earth, not to the surface of the Earth, but to the center of the Earth. And that's important for being able to measure altitude. So the ephemeris is used by the GPS receiver's algorithms to define the exact satellite position at any given time. And then the CA code gives an approximate range. And it takes correction information from the navigation message from the satellites, and there it's able to give us a quite accurate range from the receiver's antenna to the satellite. That allows us to establish our position on a sphere for each single satellite. So when we combine up to four satellites, we can get a 3-dimensional fix, and that's called the trilateration method. So using the navigation message for tunnels and underground areas. So what we need to be able to do is allow the receiver to calculate its position in those areas by providing it with a modified CA code. And that CA code is modified for the position of any radiating point that we're going to use. So by tracking the SV stands for space field, by the way. So by tracking the satellite coordinates, the received CA code can be shifted in time to provide the precise trilateration calculation for any position. So once we do that, we recompile and then we can radiate throughout the area of interest. There's a major requirement in terms of being able to have a precise time throughout the entire network. Because all calculations are based upon time and its relevance to universal time code. So we need to make sure that we have very accurate time throughout the network. And this has always been the major challenge in being able to produce underground GNSS signals. If we don't have accurate time in the receiver, then we'll have an inaccurate position calculation. Also, if you've got multiple radiating points and there is a significant time difference between each of those, then you can generate your own multipath interference at the receiver. So the challenge is in avoiding this type of spoofing impact, we have to ensure that from every radiating point, that our time synchronization is well within the 500 nanoseconds. And that each satellite's identification and its pseudo-random numbers exactly match the overhead satellites. So that's the major challenge in creating these types of systems. So just as an example of how what a system like this would look like, we can break it down into two areas. One is the signal acquisition, and the other one is the signal distribution. So in signal acquisition, we capture the signal, we digitize it, process it, and then we regenerate it with its modified CA code, and then we distribute that over fiber optic network. So the main components on the signal capture side, of course, we use external specialized timing antennas to make sure that we have very clean signals. We don't want to have that antenna with blocked sky, because we want to be able to receive all the satellites overhead. We use a Grandmaster position time protocol clock and time server. We then use a GNSS receiver to extract the three elements of the satellite signals that are required, including the navigation message. Then what we do is we take the navigation message, we take the CA code, we remove what's being received from the satellites. We then adjust that code to what's required for each individual radiating point in our area of interest. And then we recompile that navigation message, and then we send out over fiber optic network out into the area. At each radiating point, we then convert the fiber optic back into the RF signal, and that signal coming out of those radiating is exactly the GPS frequency and the GPS messages, as if you're standing outside in open sky. For the radiating points, we use passive GNSS antennas, and this is quite a critical area, because by ensuring that we can manage both the RF field and the RF pattern from those antennas, it allows us to give the best coverage throughout different areas, especially if they're of different shapes. Also, we can turn them into directional where required. But from one radiating point to the other, we need to make sure that we have a propagation delay less than 50 nanoseconds. So the NoSky system, it's fully configurable for the length, width, and depth of underground areas, because we have total control over each of those radiating points, whether it be the RF power, whether it be the propagation delay, whether it be the RF field pattern itself. So as a vehicle travels along in the tunnel area, its GPS receiver will pick up the signals from the first radiating point, and then the next, and so on. As it passes underneath each antenna, the signal to noise ratio will change for each individual satellite signal, and so the receiver We'll actually use a blending of signal from different points. And this is a very key benefit in the system. Instead of just picking up a point when it's directly under a radiating point, it actually will blend the signals, and it will give position reports in between each of the radiating points. So we're actually being able to achieve a positional accuracy of 2 meters. Now, a standard GPS receiver standing outside in open sky will give you something like 2.5 meters, 50% probability. So our system is able to actually improve upon that. Just in talking about the environment and our own test facility. So this is an image of our premises, which has an undercover car park, which we use for our testing. The red line represents one side of the car park, and when we're testing, we drive through that close to that red line. We have a lot of interference in this area from overhead satellites, reflected signals, and so our system had to manage that level of interference. This is an image of driving through the car park area with the NoSky system turned off. So you can see there's a lot of points at the entrance at one end and at the exit at the other end. We then turn on the system, and this is the result that we get. There is a little bit of shifting, which in the line, not because the vehicle changed its heading. It's actually because of the amount of reflected signal coming in there. But it's all well within 2 meters from the actual path that the vehicle took. There is a key requirement from the ACMA in regards to the use of GNSS repeaters or simulators. And a new version of the licensing has now been released. And we had to do a number of tests to show that we met all of these requirements. And I'm happy to say that we passed all of that. And that's the end of the presentation. So if there's any questions, we keep those until the end. Okay, thank you. And I'll hand back to Chris now.